learn like a pro.
All right, let's talk about sound. Today, we're going to strip it down to its bare bones essentials. We're going to take a journey to understand the pure physics of how a simple little vibration can become the whole world of sound that you and I experience every single day. Let's get into it.
So here's the big question that drives everything. A guitar string gets plucked, someone speaks, a book hits the floor. How does that initial physical action travel totally invisibly through the air and end up in your ear? What's the actual mechanical process going on?
To figure that out, we're going to follow a really simple mechanical chain of events. We'll start at the origin, where the sound energy is first created. Then, we'll look at its propagation, how that energy actually moves through something. If we can understand these two phases, we've basically cracked the code on the physics of sound. So let's build this out, piece by piece. Okay, let's dive into phase one, the origin. Every single sound, I mean everything, from a tiny whisper to a massive sonic boom, has the exact same non-negotiable starting point, a physical vibration.
And this is the most crucial point to get right away. Sound is just mechanical energy. It's not some kind of magic. It is born from physical motion. A tuning fork wiggles back and forth. Your vocal cords oscillate. A speaker cone physically pushes the air. If you don't have that initial vibration, you have silence. It's really that simple.
Now, what's really cool is the type of wave this vibration creates. It's a longitudinal wave. The best way to picture this is with a slinky. If you push the end of a slinky, you see that pulse travel all the way down its length, right? The coils themselves just move back and forth, parallel to the direction the energy is going. That is exactly how sound works. It's not like an ocean wave that goes up and down.
So a vibration creates this wave of energy. But, and this is a huge but, that energy can't just travel through nothing. And that brings us to the second critical link in our chain, what I call the medium mandate.
Okay, so the vibration happened. We've created a pulse of energy. The tuning fork is moving. But how does that movement actually get from point A to point B? What's carrying it?
And this beautifully simple experiment gives us the answer. This is the classic bell jar setup. You put a ringing bell inside a glass jar. With normal air inside, you hear it, no problem. But then you start pumping the air out. As those air particles disappear, the sound gets fainter and fainter until complete silence. The bell is still physically ringing. You can see it, but the sound just can't get to you.
So the conclusion here is unavoidable. Sound isn't some independent thing that flies through the air. It absolutely, 100% requires a medium, a substance with particles, like a solid, a liquid, or a gas, to travel. It's why in the vacuum of space, where there are no particles to carry the vibration, there's just silence.
Okay, so we know sound needs particles to travel, but what is actually happening to those particles? Let's take a look at the architecture of the wave itself.
So as that vibrating source, say a speaker cone, pushes forward and pulls back, it creates a chain reaction in the particles around it. This isn't like a gust of wind. The air particles themselves don't travel very far. They just bump into their neighbors, which bump into their neighbors, passing the energy along in this repeating pattern.
The first part of this pattern is what we call a compression. This is the moment the vibrating source pushes forward, and it literally squishes the air particles together. This creates a little temporary zone of high pressure.
And then, on the flip side, you get the rarefaction. This happens when the vibrating source pulls back. It leaves behind a space where the particles are spread farther apart, and that creates a zone of low pressure. That's literally all sound is, just a repeating series of these compressions and rarefactions traveling through a medium.
So, if sound is just a chain reaction of particles bumping into each other, kind of like dominoes falling, then how fast do those dominoes actually fall? This brings us to the speed of sound.
Well, the answer depends completely on what the dominoes are made of. I mean, just look at the difference here. In air, sound is cruising along at about 330 meters per second. Put it in water, and it's suddenly over 4 times faster. And in solid steel, it is a blistering 6,000 meters per second. So what's the deal? Why such a huge difference?
It all comes down to proximity. How close are the particles to each other? In a gas like air, they're really far apart, so it takes a little bit of time for one to travel and bump into the next one. But in a solid like steel, the atoms are packed incredibly tight in this rigid structure. So when one atom vibrates, the energy is transferred almost instantly to its neighbor. It's just a way more efficient delivery system for that energy.
Now, this all makes sense on paper, but how do we actually prove it? I mean, how can you measure the speed of something you can't even see? Well, let's look at a really simple but elegant experiment.
The setup is really straightforward. You get two people, and you put them a known distance apart. Let's say 900 meters to make it easy. Person 1 fires a starting pistol. Person 2 starts a stopwatch the instant they see the flash of light, and they stop it the instant they hear the bang.
Now, the whole key to this experiment is the gigantic difference between the speed of light and the speed of sound. The flash from that pistol, it arrives almost instantly. Light is just that fast. But the sound is much, much slower. It takes a measurable amount of time to cover that 900 meters. That delay you measure on the stopwatch is the sound's travel time.
Of course, to be accurate, you never just do an experiment once. You repeat it multiple times. And as you can see from this data, the times are incredibly consistent, right? They're all hovering right around 2.71 seconds. By taking the average of all these tries, we can smooth out any tiny human errors in starting and stopping the watch.
And now for the simple math. We've got our distance, 900 meters, and we have our average time, 2.71 seconds. We just divide the distance by the time, and what do we get? 332 meters per second. It's a real-world measurement that perfectly confirms the theoretical speed of sound in air. It works!
And this really gets to the core takeaway of this whole thing. Sound isn't some mystical force floating around. It's a physical, mechanical process, a chain of events that is completely dependent on the matter it has to work with.
This diagram just ties it all together so perfectly. You simply cannot have sound without all three of these pillars. You have to have an origin, that initial vibration. You have to have a medium, the particles that carry it. And the specific nature of that medium is what decides the final velocity. They are totally interconnected. You take away any one of those pillars, and the entire structure of sound just collapses.
So, I'll leave you with a final thought to chew on. Now that you understand this mechanical architecture, think about how you could apply it. If you were an engineer who wanted to design a soundproof wall, what kind of properties would you give it? How would you play with particle density? And on the other hand, how would you build a concert hall to carry sound perfectly to every seat? The physics we've just broken down, those are the exact tools they use to do it. Thanks for watching.